Okay, hello everyone. Today we are going to look at a Leet Code problem, edit distance. So you are given two strings, word1 and word2, and you need to return the minimum number of operations that is required to convert word1 to word2. Now you have the following three operations that you can do. You can either insert a character, delete a character, or replace a character. This is Leet Code problem number 72. So here they have given an example. You have word 1, which is horse, word 2, which is Ross. You need to convert this word horse to Ross using one of this different operations. You can use any of this operation and you can convert. And each operation is counted as one operation, and you need to maintain a count of total number of operations that you did to convert horse to Ross. So here the minimum number of operations that's required is 3 to convert horse to Ross. Another example is word 1 is intention and word 2 is execution. So to convert this intention to execution, the minimum number of operation required is 5. So let's look how we can solve this. So we are given the word horse. Okay, so we are given word horse, that is our word 1. Okay, another word that we are given is Ross, which is our word 2. Now we need to convert this word 1 to word 2, and the operation that we can perform is we can perform insert operation. So we can insert a character, we can delete a character, or we can replace the character. Okay, so now the size of this word 1 horse is n is equal to, let's say the index start from 0, so n is equal to 4, and here the size of word 2 m is equal to 2. So now when you think of a brute force way of converting horse to Ross, what you gonna do? So if I think of a brute force way, I'll try all three operation: insert, delete, and replace. So, and then I'm gonna see that uh, how many minimum operations are required. So I'm gonna try all the operation. For example, let's try with this word. Okay, so we are given horse. Okay, and my n is 4, and then I need to convert this horse to Ross, and my m is this size of the word, which is pointing to s. So if I do insert, what should I insert here in this word horse? If I'm doing an insert operation, and let's say I'm starting at this position, and I need to do insert. I need to insert a character. What is the one character that I'm gonna insert? So if I need to insert, then I'm gonna insert s, so that my this s and this s matches, right? And then once I insert s, I'm gonna decrement this pointer n, right? So in insert, I'm not going to do anything with the pointer. Oh, sorry. Just give me one sec. So uh, n, my pointer n is going to stay the same. So this is my pointer n. It's going to stay at the same position. but I'm going to decrement my M pointer. Why? Because I have matched both the character. Now let's say I'm doing delete operation. So if I'm doing delete operation, what happens then? Okay, so let's do that. So again, I have a word, this horse. So this was the insert operation. Now I'm going to do a delete operation. So I have horse and Ross. My N is pointing here. My M is pointing here. If I need to delete a character, then what I'm going to do? I'm going to delete this character E, right? So when I delete this character E, my pointer N is going to decrement, right? What happens to M? Nothing. It stays wherever it is, right? So that's delete. Now if I try a replace operation, right? So I have horse and then I have Ross. Okay. Now I'm going to try a replace operation. So I need to replace this character E with some character. So what I'm going to replace with? I need to change, convert this horse to Ross. So I'm going to replace this E with S. And now this both the characters are matching after replacement. So I need to decrement my pointer N and my pointer M. Now, so these are the three operations that I tried. So what I'm going to do, I'm going to try all three operations. And then whatever the remaining string that I have, which is, so after insert, I have this string remaining and this string, and my N is pointing here and my M is pointing here. I'll pass this string to my teams and I'll ask them, okay, now you all do the same thing that I did and give me the minimum number of operation that is required to convert this string to RO. Now, so this is insert, and for delete, I'm going to pass this string and this string to my subordinate, and I'm going to ask them that you convert, give me the minimum number of operation that is required to convert HORS to ROS. And if I did replace, then I'm going to pass this string and this string to my subordinate and ask them to convert, right? And give me the minimum number of operation. And whatever answer they give me, I'm going to add +1 for my insert, delete, or replace, whatever I did, right? Whichever is minimum, I'm going to add +1 for my operation and I'm going to return that answer. So that is a brute force way of doing it, okay? So let's try one example and let's see how we can convert this. So I have given word horse and my Ross is here. My N is pointing here and my M is pointing here. So let's say, I'm just trying random operations. So let's say I'm doing delete. Okay. So I'm going to delete the last character. So I did delete operation. And after delete, my word is HORS. My N is pointing here. My M is pointing here. Let's say now both the characters are matching. So I'm going to do nothing. I'm not going to do any operation and I'm going to decrement both my M and N. So I'm not doing any operation. My M is here, my N is here. Now I'm going to try a replace operation where I'll replace this R with O. So when I do the replace operation, I have HOS n- sorry, I'm replacing R with O. So I'll have this HOOS, right? And ROS. And once I do replace operation, I need to decrement both of my pointer, right? Now again, I'm going to try replace operation and I'm going to replace O with R. So now if I do that, then I will have HROS. I need to decrement both N and M. So this is going to point to -1. My M pointer is going to point to -1. Now that means I'm done with this string M. So that means whatever I have here in word1, I need to delete it because I have already matched, I have converted word1 to word2, and whatever characters I have here, those are the extra characters which I need to delete. So my N here is 0. So I mean the index is 0 base. So N plus 1. Those are the characters which I need to delete. So in this case, I need to delete this one character, which is S, right? So that is counted as one operation, whatever the number of characters. So it's delete. Here I'm deleting one character. So it's one operation, whatever the value of N plus 1 is. So here I'm performing 1, 2, 3, and 4 operations, right? I need to find the minimum operation, okay? So basically what we are doing here is we are given word 1, word 2, and then we have our N, and then we have our M, right? So basically what we are doing here is recursion. And recursion is always top-down approach. So our N and M are starting at the end, and then we're going to decrement, right? Now there is always a base case in the recursion. So what I'm doing is I'm doing insert a character, I'm doing delete a character, and I'm doing replace a character. I'm trying all 4 operations. So if I'm doing insert, my N stays wherever it is, and I'm decrementing M because I have already inserted that character in word 1. So that's matched. And if I'm doing delete, I have deleted a character, I need to decrement N and my M stays as it is. And when I'm doing replace, I need to decrement both N and M. And there's one more operation, okay, where the characters are matching. You don't do anything, you just decrement it. And then again, I'm doing the same thing here. Insert, delete, and replace. Same thing here, same thing here. Insert, delete, replace, insert, delete, replace. So all of them, they're gonna give me the minimum operations that is required to convert whatever the remaining word 1 is to word 2. Now from all of these 3, okay, I'm going to pick the whatever they have written me, I'm gonna pick the minimum of all, okay. So I am going to pick the minimum of all, and I'm going to add 1 for my operation. So if I have picked, if the minimum of this is delete, I'm going to add 1 for my operation, or insert 1, I'm going to add 1 for my operation, right? So how our recursive function will look like, right? So we have a recursive function. This function is returning integer, right? Because we are returning the minimum number of operations required to convert word1 to word2. And we have our word1, we have our word2, we have n and m, right? Now always the recursion has a base case, right? So what happens when n is less than 0 and m is also less than 0? So we have this word, maybe we have already converted it. So we have this word where our n is here and our m is also here. That means nothing is left in word 1, nothing is left in word 2. We have already converted. We don't require any more operation. So we are going to return 0. If our n is less than 0, that means our n is less than 0. So word 1 is done. But we still have some characters here, right? So we need to convert this word 1 to word 2. So what we're going to do? We're going to add these characters here, right? So whatever the remaining characters are there in the word 2, we just simply need to add it. So whatever the characters are there, we need to return that many operations we need to do, that many inserts we need to do. So we are going to return m plus 1. The index is 0 base. That's why we are doing plus 1. Now what happens if our m is less than 0? So our m is here less than 0. We don't have anything left here, but we still got some few characters here, right? Our n is pointing here and our m is less than 0. That means we have already converted this word 1 to word 2, but we have few extra characters here which we need to delete it. So whatever the number of that many delete operations we need to do, so we need to return that many characters, which is n plus 1. So those are all the base case that we have covered. Now what happens if both the characters are matching? We don't need to perform any operations if both the characters are matching. But if both the characters are not matching, then we need to perform the replace operation. Replace, insert or delete. So let's say the word 1 dot character at n is not equal to word 2 dot character at m. So the characters are not matching. That means we can perform a replace. But if the characters are matching, we are not performing any replace operation. We are just decrementing the n and m. Okay. So now here I'm going to return the minimum, okay, of my insert operation. I already inserted a character, so I counted that as one operation, and then I made a recursive call to my subordinate with the remaining word 1 and word 2. So once I inserted a character, my n stays as it is, but I need to decrement m because I have already inserted a matching character in word 1. Then delete minimum of, I'm going to ask my subordinate, okay, I have deleted one character, so that is counted as one operation. Now you guys go ahead and tell me what are the minimum operations required to convert word 1 to word 2. Now since I have deleted a character, I need to decrement my n, but my m stays as it is. And then minimum of this insert or minimum of this, okay, and then replace. Now replace is counted as one operation only when we have two characters not matching. If we have two characters matching, we're gonna simply decrement our n and m, right? So I'm going to ask my subordinate, okay, I have replaced it. If the characters are not matching, if the characters are matching, then um, if I have replaced it, then it's counted as one operation. But if I haven't done any replacement, the characters are matching, then that is counted as a zero operation. So I'm going to use my x, right? The x that I have initialized here, the x is 0 if the characters are matching, and the x is 1 if the characters are not matching here. I did that logic here. Okay, so now if I have replaced it, I'm gonna do n minus 1, m minus 1, and even though I haven't replaced it, if the characters are same, I still need to decrement that. So this is minimum of this. That is what I am going to return. So that is our recursion. Now, what is the time complexity for this solution? So if you look at the recursion tree, so we have our word1, word2. In this case, let's assume we have horse, and then we have Ross. Our n is 4, our m is 2, and then we are trying all the operation: insert operation, delete operation, replace operation, and again making a recursive call with. Okay, so we have a recursive function word1, word2, and when we are doing insert, I'm inserting a character in word1, so my n will stay the same. My n will stay the same, and I need to decrement my m, which is m minus 1. For delete, the recursive function will be word1, word2. I need to decrement n because I'm deleting, and m stays the same. And for replace, the recursive function will be word1, word2, n minus 1, and m minus 1. And again, I'm going to repeat the same thing: insert, delete, replace, insert, delete, replace, insert, delete, replace. So what is the time complexity? So if you look at this recursion tree, right, it has how many branches? 3 branches. Okay, and what is the height of this tree? Right, the height of this tree will be n plus m. That is the max height it can go, right? So the time complexity will be big O of the number of branches, which is 3, and the height of the tree, which is n plus m. So that is the time complexity. Now what is the space complexity? So here the space complexity will be whatever the space that we are using for recursive call stack. That means this function calls this function, this function calls this function, this function calls this function. So everything is in the stack, and once they return, it's popped out from the stack. So the maximum size of the stack will be the height of the tree, which is n plus m. So the space complexity will be n plus m. Now clearly, if you look here, this time complexity is exponential, right? So we need to come up with some better approach. But before we do that, let's code this. Let's write code for this recursive solution, and then I can show you how we can do improvement on this time complexity. So I'm going to write code here in Java. I'm going to reset my code, and I'm going to write the recursive code here. So here, so first we need to find the size of the word 1, which is word1 dot length minus 1, because we are going to start from the end of the word. Then we will find the size of word2, which is word2 dot length minus 1. Once you got the size, we need to design our recursive function. Our recursive function will return the uh, minimum operations required to convert word1 to word2. So minimum distance helper. Our recursive function will take word1, word2, n, and m. Okay, and now we are going to write our helper recursive function, which is going to return integer minimum number of operations, min distance helper, string word1, string word2, integer n, integer m. Okay, now first we are going to write our base cases. Okay, so if n is less than 0 and m is also less than 0, then we don't have anything left in the word 1 and word 2. We are done. We have matched, we have converted. So in that case, we don't need to do any operation and we are going to return 0. If n is less than 0, that means we have something in word 1 and we have already matched the word 2. There's nothing left in the word 2. So that means you need to delete all those characters. Sorry, we have nothing in word 1, n is less than 0. But we have something in word 2, so we need to append those characters, insert those characters. And the number of operation will be number of insert that we are doing, which is equal to number of characters, so m plus 1. The index starts from 0, that's why we are doing plus 1. If m is less than 0, in this case, word 2 is done. We have few characters in word 1 which we need to delete it, and it's that the delete operation will be whatever the number of characters. So we are going to return n plus 1. Same thing, the index starts from 0. And then we are going to return math dot minimum of insert, delete, and replace, right? But for replace, we need to make sure that if characters are not matching, word1 dot character at n is not matching word2 dot character at m. If the characters are not matching, that means we need to do a replace. Otherwise, we don't need to do a replace. We just decrement the counter. So first is the insert operation, which would be 1 plus, because I'm doing insert a character, so that is counted as one operation. I'm going to make a recursive call to mean distance helper. I'm going to pass word1, word2. Since I'm inserting a character, it would be I'm inserting a character, so n stays at the same position. I need to decrement m, right? So n stays at the same position, so n m minus 1, and then math dot minimum word1, word2. Now I'm deleting a character from word1, so my n is going to decrement and m is going to stay the same. Math dot minimum of 1 plus the delete operation. right? And then now the replace operation, which will be x plus if the characters are matching. X is 0, if not matching, x is 1 because we are doing replace, so that's counted as one operation. Let me do it here. X plus mean distance helper word1 word2, and I'm replacing character in word1, so I'm going, my both the characters are matching, so I'm going to decrement my both the pointers. So that is the recursive code. Now let's run it. Oh, I missed a bracket somewhere. X plus. Okay, so here, let's see. We have this bracket. Okay, mean distance helper word1 x plus this. This is for that, and this is for that mean. Okay, I just missed one bracket. So this is clearly so here we are seeing that time limit exceeded. The reason for this is because we have time complexity which is exponential, and because of that we are getting this time limit exceeded. So we clearly need to design a solution where so this is not an optimal solution. It is a solution, but it is not an optimal solution. So let's work on designing the optimal solution. So let's go here and let me do this. Okay, so let me create a new document and let's try to design the optimal solution. Okay, okay, so now what we came up with we came up with a recursive solution. And the time complexity was O of 3 raised to n plus m, which is not optimal, it's exponential. So now if you think, what we can think of is the recursive tree that we saw, right? For this word horse, Ross, this is 4, this is 2. So if I'm doing insert, I'll have horse, so I'm inserting a character, I think, and then Ross, horse will become S, and then I have this 4 and this 1, right? And if I'm deleting, then I have H O R S R O S, and I'm deleting a character, so this becomes 3, this becomes 2, and if I'm replacing, then H O R S S R O S, this becomes 3, this becomes 1. Okay, now let's try again. So here again I'm doing an insert, right? So I'm going to insert, so now my n is here and m is here, so now I'm going to insert O, okay, at that position. So HORSEO, and here ROS, and then I'm going to decrement this to 0. And if I try delete here, so I'm deleting S, so what I'm left with is horse, rose. I have deleted S, so now, sorry, I'm deleting E. Sorry, I'm so sorry. I'm deleting E, so it's pointing, my N is pointing here, so I'm deleting E. So it's gonna become this, okay? And then since I'm deleting, I need to decrement N, which will be 3, and this is going to remain 1. Now, if you look at this particular step, right, and this particular step, right? So here there is a repetition. This subproblem are same. So that is called overlapping subproblem. So the answer that you're gonna get from this, both the problem is going to be same. So why we need to repeat it? We don't need to repeat this. And so we have an overlapping subproblem. So what we can do to optimize this solution? So one thing that we can do is we can do a dynamic programming. So whenever you have overlapping subproblem, you need to go for a dynamic programming approach. Now dynamic programming is a bottom-up approach. Bottom-up approach. Recursion was top-down. So now we already have a recursive solution that we have written. Now to convert that to a DP solution, what you need is, you can, first of all, you can never write a DP solution without a recursive solution. So you need to have a recursive solution. And once you have a recursive solution, you just need to take that solution and convert it to DP. You can never ever write a direct DP solution. So our recursive solution was like this. We have word1, word2, we have n, we have m, and then we have a base case n less than 0 and m less than 0. Then we were returning 0, n less than 0. Then we were returning m plus 1. And then here m less than 0, we were returning n plus 1. And then we were returning 1 plus, we were making a recursive call to the function. This is insert. We were returning the minimum. And again making a recursive call for delete. And then replace. Now to convert this to a DP solution, what you need to do is, first of all, we need to construct a DP table. Now you need to find out that my DP table, should it be 2 dimension, 1 dimension, how you can find that? So you can always think that in this recursive function, what are the parameters that are changing? So when we make a recursive call, what are the things that's changing? It's n and m. So we have 2 parameters that are changing. So our DP table will be a 2D table. Okay. Now, what is the return type of this recursive function? It's integer. So we need 2D int table. Now, what should be the size of this table? All different values that n and m can have. So the n can have values from 0 to n and m can have 0 to m, right? Now we cannot have a negative index, so we're gonna consider it 0. So now let's create a DP table. Okay. Okay. So I have this DP table. What is the size of my first word? 5, right? Horse, right? So 5. So my size of the DP table will be n plus 1. Sorry, I'm so sorry. The size of my DP table will be n plus 1 cross m plus 1, right? Why? Because, just give me one sec, let me draw this. Okay. Because we will have this word horse and we will have this word Ross. And this is our base case. When m is less than 0, n is less than 0. That means when m and here, this is our n and this is our m. Okay. So when m and n both are 0, right? When both are 0, that means we don't have anything left in both the words. When we don't have anything left in both the words, that means we have matched the word and we don't require any operation. It's like our base case where n is less than 0, m is less than 0. Now in this matrix, we cannot have -1 index, so we are just starting with a 0 index. So this is our base case where we'll put 0. Now this is also our base case where our m is 0. That means we have nothing left in this word 2. But we have this character left in the word 1. That means we have matched all of the remaining character, but we have this character left. So what we're going to do, we're going to remove this, right? So whatever the size of n is, we're going to remove it. So here the n is 1. So we're going to remove one character. So it requires one operation. Here 2, 3, 4, 5. This is nothing but our base case. When m is less than 0, we return n plus 1. Here the index is not starting from 0, so it's just n. Here we need to remove one character, two character, three character. Here we need to insert a character. Here n is 0. Okay, the value of n is 0 here, right? When n is 0, we don't have any character left in word 1, right? But we have few characters left in m, so we need to insert those characters, whatever the size of m is. So here 1, 2, 3. That's our base case, right? So we're going to fill our base case and then we can iterate this table either row by row in a row major order, or we can also iterate in a column major order. Now it's always preferable to iterate this table in a row major order because it is more cache friendly. So when you iterate in a row major order, it already fetches few more rows, the cache. If you are querying for this row, it will fetch 10 rows down the line. So it is more cache friendly operation. And here you can iterate in row major or column major order, any order, because we just require the information from a previous row or a previous column. So our DP, after filling the base case, our DP of I, J will be nothing but the minimum of insert, which is DP of, just take the recursive function call that we were doing for insert and convert it to a DP. So it would be I, J minus 1, 1 plus delete. So I minus 1, J, and replace, which would be X plus DP of I minus 1, J minus 1. That's it. and our answer will be here in the last cell. This cell will have our answer. Okay, because dp of m and n, this will hold our answer, the minimum operation required to convert this word to horse to Ross. This will have our final answer and we're going to return that answer. So what is the time complexity of this solution? So what we are going is we are just iterating this matrix. So our time complexity is O of mn, that's the size of the matrix. And what is the space complexity? We are just creating a matrix. So same, the size of matrix, which is mn, that's our space complexity. Right, so this we have, we went from exponential, we reduced time complexity from exponential to mn, so that's a very good improvement, right? Although it's a quadratic, but it's still, we decreased it, right? So um, let's write the code for this dp solution in the same place where we have written the code for this one. So I'm going to minimize this and then I'm going to reset my code to a default code definition, and my code is in Java, and now I'm going to write a dp solution for this one. Okay, so now here my n, what is the size of word1? Word1 dot length, which is 5. I'm just considering that horse and Ross example. M is equal to word2 dot length, which is 3. And then I'm going to create a 2D dp array, which would be of the size n plus 1 m plus 1, right? And then I'm going to iterate the dp table. I is equal to 0, I less than equal to n, I plus plus. I'm iterating in a row measure order. J is equal to 0, j less than equal to m, j plus plus. And then I'm going to fill in my base case first. I'm going to check for my base case. So if I is equal to 0 and my j is also equal to 0, that means that is a first cell, nothing is left in word1 and word2. I have already converted. I don't require any further operation. I require 0 operation, so dp of ij is 0. Else if only I is equal to 0, in that case dp of I j will be equal to j plus 1, that many inserts I need to do. Else if j is equal to 0, that many deletes I need to do. So dp of I and j is equal to I plus 1. And in the last case, dp of I j, before that I need to do that x thing. So integer x is equal to 0 if word1 dot character at I is not matching word2 dot character at j, then I need to do a replace operation. So my x will be equal to 1 and dp of ij is equal to math dot min of my insert operation, which is dp of I j minus 1 math dot min delete operation dp of I minus 1j, and then comma x plus dp of replace, or if it's same character, I'm not replacing, just decrementing. So that will be my dp of ij, and outside the for loop I'm going to return the last cell, which would be n and m, right? Let's submit this code and let's see what the result is. I forgot semicolon on line 11. Oh, that's my comment. I need to return this, right? Where I'm returning this. Okay, that is still a for loop. Okay, okay, got it. So that was my else closing bracket, and then I have two for loop closing bracket, and now this should work. Oh yeah, so here I'm matching the character, but here the index is 1, 2, 3, 4, and the character would be at one lesser index. So if I'm matching the word H, then its index in the word will be one less. H will be 1. Let me show you. Let me show you this. Let me show you. So if I'm matching this H, so its position in the string would be 0, not 1. So I need to do -1. And then what we have, if word1 is empty and word2 is A, so I need to convert word1 to word, put as 2, expected is 1. So that's 0. Oh, I don't need to do j plus 1 here because so here the number of characters will be the same as the index because our index is not starting from 0. So if the index is 1, then there are only, sorry, if the index is 2, then we need to insert or remove 2 characters. So that's the case. And yeah, the solution is accepted. So these were the two approaches for this edit distance problem, the recursive approach and the DP approach. Always go for the recursive approach first and then go with the DP approach. In the DP approach, you need to cover the base case, you need to iterate it, you need a DP table, but make sure you work with this index. The index are starting with 0, -1, whatever it is. That's the only thing that you need to work out. Other than that, it's fairly the same. The copy